Welcome to the third video of the example for combinations of loads. In this one, we'll go through finding all of the normal stresses. So stresses due to the axial load, stresses due to bending, and stresses due to the pressure vessel nature of what we're looking at. When we're trying to determine the stresses at point H, we're going to start with the normal stresses. These will be caused by bending moment and axial loads. Let's start with axial loads. That's certainly the easiest stress equation to think about. So that's going to be caused by force over area. In this case, we've got 20 kilonewtons in the y direction, and we can divide that by our cross-sectional area, which we said was 1,810 square millimeters. And that's going to end up giving us 0.011 megapascals, or kilonewtons per square millimeter. I'm going to use those throughout. Probably could have gotten away with regular pascals, but it'll be about the same. Yeah, let's use megapascals. Now let's think about bending moment in the x direction. So bending moment about the x direction, that's going to be caused by this one right here. You already know what the moment is. The moment about the x direction, so I'm going to call that bend x. That's going to be equal to moment about the x direction times, our distance from the centroid is just the radius, right? And then we'll divide that by our second moment of inertia, which we said was, I right there. And that's going to end up being for us, we said that was 4,000 Newton meter, or kilonewton millimeter, if you prefer that. Our radius is going to be 51 millimeters. We divide that by our ludicrously large value for our second moment, 2,092,753 millimeters to the fourth. I realize that we don't have to use millimeters to the fourth for everything. We could use meters to the fourth. That would be a much smaller number, but we'd still want to have quite a few decimal places for that. And that's going to end up giving us 0.09748 megapascals. Now, both this and the moment due to it are going to cause compression at point H, right? So in this case, it was just because we've got a compression load. In this case, it's about where we are. But we are ending up with compression from both of those. Now, bending about the z-axis is also something we need to think about, because we do have bending moment about the z-axis. However, when we do that one, it's going to still be normal stress in the y direction. The moment about z, that is going to be something. But our distance, right, our in the case of moment about the z-axis, it's going to be x. I wrote r right there, but we could really also accurately describe that as Z, is what it ought to be called. But it's not going to be the radius. In this case, it'll be 0. So that'll be 0 because x will be 0. Right, our distance away from the neutral axis of this circle in the x direction is going to be 0 at point H. So we're good. We're golden as far as that goes. So that's all of the that's the two normal ways that we would find normal stress. We do, however, also have the fact that it's a pressure vessel, right? And so we're going to have let's specify that these were in the y direction, those normal forces, because we're also going to have normal stresses from the pressure vessel, and those will be in both the y and the x direction. So let's do the longitudinal stress first. And that's going to be stress in the y direction, right? For longitudinal is up and down there. And that's going to be equal to 1/2 the pressure times the radius divided by the thickness. Or in this case, we were given 0.08 megapascals times 45 millimeters is our inner radius. Remember, in the case of thin-walled pressure vessels, we deal with the inner radius. Now, normally, because of the thin part of a thin-walled pressure vessel, it's not a big deal. In this case, it's pretty significant. So do be careful of that. Divided by 2, because this is the longitudinal one. Careful about that one. And then our thickness is going to be 6 millimeters. So this is going to give us 0.3 megapascals, and that's tension in the y direction. And we're also going to have hoop stresses. Okay, and those are going to be at point H. Those are going to be in the x direction. Okay, as we try to expand the cylinder outward, and it's going to be in the x direction when we're at point H. Now when we're at point K, that's going to be in the z direction. Still not the y direction though. So this is going to be in the x direction at point H, and that's going to be P, the pressure, times the inner radius divided by the thickness, and in that case, it's going to be 0.08 megapascals. That's the pressure. 45 millimeters divided by 6 millimeters, and would you believe that it ends up being 0.6 megapascals. Also tensile, but this one in the x direction, not the y direction, which is what we were dealing with for all the other ones. So for this, now we've got all of these sources of normal stress, which we can, which we need for this. Let's move on to the shear stress.